drift velocity and current density. The figure shows a section of metal wire of length L and cross-sectional area A. Conventional charges, each having the elementary charge E, are also shown. The charge density, that is the number of charge carriers per cubic meter of the wire, is given by N. An electric field has been imposed through the wire by connecting the wire into a circuit that has a battery. The direction of the electric field is shown by the thick solid arrow. So that's right there in the upper right corner. Which side of the wire is connected to or closest to the positive battery terminal? Well, if the electric field is traveling to the right, then the left side of this wire must be connected to the positive battery terminal, and the right side must be connected to the negative. In the circle in the upper right corner, draw an arrow showing the direction conventional charge flows. In the other one, draw an arrow showing the direction that conduction electrons flow. Conventional charge is going to flow in the direction of the electric field. Conduction electrons will flow opposite the electric field. Because of the huge number of atoms and the swarms of non-conduction electrons in the metal, the conduction electrons cannot move unimpeded through the metal lattice in response to the imposed electric field. They bounce around mostly randomly, but over time, they tend to drift in the direction we indicated in Part B, which you can see there at the top of the screen is to the left, and with a particular drift velocity, v sub d. This motion of the conduction electrons is indistinguishable from conventional, i.e. positive charge, drifting in the opposite direction at the same speed. So, in a certain time t, all of the conventional charges that started within the shaded portion of the wire will have moved out of the shaded portion. Write an equation for drift velocity v sub d based on the distance shown in the figure and this amount of time t. In other words, in the figure here at the top, all of these charges will have moved out of that region in a certain amount of time. And so the drift velocity, one equation for it, is the length of that little section of wire divided by time. Velocity is distance divided by time. We're going to need that here in just a little bit. The total amount of conventional charge that passes out of or into the shaded region in the time t is the charge q that's contained within that region's volume. Write an equation for this amount of charge. In other words, what is q equal to? All right, well, q is equal to the amount of charge. And what do we know? Let's see, let's just start using some variables that we have. N is the number of charges per cubic meter. That's the volume charge density. Now, that isn't the same thing as the amount of charge, because the amount of charge needs to be in coulombs, and this is a number of charges. So let's see, what else do we know? We know that elementary charge is some amount of coulombs per charge. Okay, this is a good thing because that means that that unit will cancel that unit if we multiply those two together. Now, charge, as we know, is in coulombs. So that means that we need coulombs on the right side, which means we need to get rid of this cubic meters. In terms of the variables we have, how can we get rid of cubic meters? Can't we multiply by the cross-sectional area of this thing? And that would be meters squared, wouldn't it? And then if we multiply by the length, that would be meters also. And there go your meter units. All right, so the product of those four things will give us the total amount of charge that's inside that region. The current I can be defined as charge per time. Write the equation for that. Charge per time, the amount of charge that flows in a given amount of time. Combine the parts C through E answers to get an expression for the current I in terms of the drift velocity. So here was our answer to part C, and then we can see the answers to D and E. So now we need to combine these to get an expression for I. Let's start with this. I is Q over T. And at the top of the screen, charge is N times the elementary charge times the area times the length. And we also need to get the drift velocity in here. So how are we going to do that? Well, it looks to me like L divided by T is equal to the drift velocity. So there's L in the numerator and there's T in the denominator. That's the drift velocity right there. I think we got N times E times A times VD. And the way I usually write that, I usually write it in this order. Of course, it doesn't matter what the order is, but that's easy for me to remember. Knave. The quantity current density, J, is defined as current per area. The equation for that then is going to be current density is current per area. Combine parts F and G to obtain a new expression for current density. There was our answer to part F. And if we combine that with this equation here, it looks like Nave is going to go in the numerator and then the A cancels. So I think N times the drift velocity times the elementary charge. Let's show now that our part H answer is dimensionally consistent. Current density is I divided by A. So that means the left side of this current is amps. I'll write that out, amps, because we're going to change that in a minute, I think, divided by square meters. Well, an amp is a coulomb per second. So the left side becomes that. What do we have on the right side? On the right side, we have number of charges per cubic meter. Let me put a question mark over that equal sign, make sure we're checking this out. So N is charges per cubic meter. Drift speed is going to be meters per second, and the elementary charge is some number of coulombs per charge. What happens there? Charge goes away. One of those meters gets canceled. Oh, look at that. Pretty neat. Those units do agree.